So, vibrations and waves. There is a rotating or a swinging pendulum. You'll note that every swing is following the exact same path, and so it can be considered a vibration. It's vibrating back and forth around an equilibrium point. So it's called vibrational motion. What is the equilibrium point, or where is it? Right? At the bottom, right? If you might imagine if there were friction here, this thing would slow to a stop, and it would stop right at the bottom. So that is the equilibrium point right there. And so it's oscillating back and forth, right, around that point. Okay? Without friction, it'll just keep going. Now, each trip back and forth, because there is no friction, is going to take the same amount of time. Okay, we talked about the period of something's motion when we talked about circular motion. That's when we first used the term period to describe that time period to do one complete rotation. So now it's not a rotation, it's just a cycle. A back and forth is one cycle. And the time it takes to do that is the period. So when that is a repeating regular cycle, it's called periodic motion.
We'll use this glider floating on a cushion of air and these springs to investigate simple harmonic motion. If a spring is attached to each end of a glider, the glider will oscillate back and forth on the track. What will happen to the period of oscillation if we double the mass of the glider?
So first off, I just want you to understand that motion, because that's what we're going to be talking about, that back and forth motion. Hopefully, do you realize or see that that's the same as a pendulum, right? The pendulum we saw, this is doing the same thing, okay? That's the motion we want to look at. But now, what they've done is they've increased the mass of the glider. What's going to happen to the period, you suppose? Longer, right? It's going to take longer because now there's more inertia. You got to change the direction of that mass.
The top half of the screen shows the original arrangement, while the bottom half shows the glider with twice the mass. The period has increased. What will happen to the period if we add another spring to each end of the glider instead of more mass? The top half of the screen now shows the original setup, while the bottom half shows the glider with another set of springs attached. The period has now decreased. To show the form of this type of motion, we will mark one point on the glider and use it to draw a graph of position versus time.
And so what do you see there? A wave, right? That's where we're going to be going with all this, is waves. So by understanding this motion, we're going to build our knowledge and vocabulary to get to talking about. So that's what this picture is. It's a mass, but it's attached to a spring. Okay, and the spring in the top picture here is at what's called its equilibrium position. It's not stretched, it's not compressed. So it's at equilibrium. It's not exerting any force. Now, if I were to grab the mass and say pull it this way, like in this picture, the spring will stretch. And when the spring stretches, it starts to exert a force back on the mass to bring itself back to equilibrium, right? To bring the mass back to the equilibrium position. So whether we compress it or stretch it, here we're compressing it, the spring will exert a force to come back to its equilibrium position. Okay, the force that the spring exerts is called the restoring force, because that's what it's trying to do, is restore itself back to its original shape. Now, in the top picture, it's at equilibrium position, so the position would be x. We're going to use the variable x for position, is at 0, and there's no force applied. Now, as I pull the mass or I compress it, the further I get from equilibrium, the greater is the restoring force. So you might imagine, I'll pass these springs out at the end of class so you can mess around with them, but right now, this spring is not exerting any restoring force. But if I pull on it, now it begins to exert a force on me, right? Think about, I'll keep this hand stationary. So now it's exerting a force on my right hand. But if I stretch it even more, right, it'll exert more force. If I stretch it more, it exerts more force, right? Until I break it, right? But I don't want to do that. But the more I stretch it, the greater is the force it tries to restore me with, right, for the restoring force. So the further I move it in either direction, the greater is the restoring force. And experimentally, it's been determined that that restoring force will be directly proportional to the displacement from the equilibrium position. So it's more than just you stretch it and the more you stretch it, the more force. Yes, that's true, but there's a numerical relationship there. So that's what I want to look at on the board here. And what I'm going to do is I'm going to grab the mass and pull it to the right. So when I do that, the spring ends up stretching. So now we have a stretch spring. I'll stretch it to about there. So if this was x equals 0, now this will be x equals 1. And now there's a restoring force kicked in. Which way is the restoring force? This way, right? To the left. It's trying to pull it back to position. So F is the restoring force, and we'll give it a value, say, of 10 newtons. 10 newtons to the left. If I pull it even more, so let's do another scenario where I pull it even further. Spring stretches more, maybe to here. And here's still where x equals 0. Now it's at x equals 2. What's the restoring force going to be?
20.
20, right? So it will have increased by double the amount. So now F equals 20 newtons. Right? That's what that last statement is saying. It's directly proportional to the displacement. If I go out to 3, it would be 30, 4, 40. Likewise, if I compress it by 1, it would be 10 that way. If I compress it by 2, 20, okay? The direct proportion.
We'll show how the stretch of a spring varies with the applied force, using this hanging spring and a set of weights. With no weights added, the bottom of the spring is here. Here is the spring extension with 10 newtons of added weight. $20 newtons. $30 newtons. Now we'll add the same set of masses to a different spring, leaving the markings from the first spring on the screen for comparison. 10 newtons. 20 newtons. 30 newtons.
Newton per meter, Newton meter. So K is called the spring constant, as the units of newtons per meter. So what it says is that this spring, for a given amount of stretch, will give you this many newtons of force, in restoring force. So we have this spring, which is called a snaky. Okay. See, I'm stretching it. It's giving me a certain amount of force for a given amount of displacement. I have this spring.
How do you spell snaky?
S-N-A-K-Y, which is called a slinky. Would it have a higher spring constant than the snaky or a lower one? Lower, right? For a given amount of stretch, you know how easy it is to stretch a slinky. Not getting as much force out. So it's, for a given amount of stretch, it's a very low spring constant. I have this spring. Anybody know what this is from?
A bed? Like a cot?
No. From a garage door.
Physics catalog?
No. This is very hard to stretch. I'll pass all these around. But is this a high spring constant or a low? High, right? Very little bit of stretch and a whole lot of force. All right, so it's a very high spring constant. So those are just an example, 3 different springs with different spring constants. The stiffer spring has the largest value of K. More force to stretch it. That's the garage door spring. There's a minus sign built into the Hooke's law equation. And it's there because the restoring force is always opposite the direction of displacement. So if I, for example, take this box and I pull it to the right, the displacement is positive. What's the restoring force's sign? Negative, right? So by having the negative there, when you have a positive x, you have a negative f. When you have a negative x, meaning it's compressed beyond, to the left of the equilibrium point, then you have a positive f. Okay, so that's what that's doing. So the spring is actually pulling up here, right? So the restoring force is up. Now, simple equation. F equals negative kx. The force is the weight of potatoes. Right? We're in equilibrium, so we know that that is what the restoring force is. The spring is pulling up with that much force. You got your negative k, you leave your negative there as part of the equation. And it's stretched below its equilibrium point. So that's negative 0.18 meters. And so your K comes out to about 311 newtons